Stability of alkenes. Hydrogenation. Alkene hydrogenation is the addition of hydrogen gas, H2, to an alkene which saturates the bond and forms an alkane. Alkene hydrogenation reactions require a transition metal catalyst, such as point or PD, to speed up the reaction. The hydrogenation reaction is used in this section to investigate the stability of alkenes. Hydrogenation reactions are exothermic, and the enthalpy change in this reaction is called the heat of hydrogenation, delta H degree hydrogen. Since the double bond is breaking in this reaction, the energy released during hydrogenation is proportional to the energy in the double bond of the molecule. By comparing the heat of hydrogenations from a series of alkenes that produce the same alkane, a quantitative measure of relative alkene stabilities can be produced. These experiments will lead to a general understanding of structural features which tend to stabilize or destabilize alkenes. The catalyst. A catalyst increases the reaction rate by lowering the activation energy of the reaction. Although the catalyst is not consumed in the reaction, it is required to accelerate the reaction sufficiently to be observed in a reasonable amount of time. Catalysts commonly used in alkene hydrogenation are platinum, palladium, and nickel. The metal catalyst acts as a surface on which the reaction takes place. This increases the rate With this catalyst present, the sigma bond of H2 breaks, and the two hydrogen atoms instead bind to the metal, C2 in the figure below. The pi bond of the alkene weakens as it also interacts with the metal. Since both the reactants are bound to the metal catalyst, the hydrogen atoms can easily add, one at a time, to the previously double-bonded carbons, C4 and 5 below. The position of both of the reactants bound to the catalyst makes it so the hydrogen atoms are only exposed to one side of the alkene. This explains why the hydrogen atoms add to the same side of the molecule, called syn addition. Heats of hydrogenation. The stability of alkene can be determined by measuring the amount of energy associated with the hydrogenation of the molecule. Since the double bond is breaking in this reaction, the energy released in hydrogenation is proportional to the energy in the double bond of the molecule. This is a useful tool because heat of hydrogenation can be measured very accurately. -30 kcal/mol. Stability is simply a measure of energy. Lower energy molecules are more stable than higher energy molecules. They have a lower heat of hydrogenation. Cis/trans isomers. During cis and trans isomers of an alkene, the cis isomer tends to be less stable due to the molecular crowding created non-bonding interaction between two alkyl groups on the same side of the double bond. The crowding creates steric strain, which distorts bond angles, creating less effective bond orbital overlap and destabilizing the molecule. The steric strain has previously been seen in gauche interactions in Newman projections and 1,3 diaxial interactions in substituted cyclohexanes. Steric strain is directly related to the size of the species being crowded. The difference in energy between cis and trans 2-butene is 5 kilojoules per mole. However, this difference would be greater if the larger group were being held in the cis position. 40 kilojoules per mole of steric strain. Cis tertiary butyl groups can create. See the following isomers of butene.